And all these little atoms form Jack. So there's a lot of them. And there's this thing called space, which separates the atoms. And at the beginning of the universe, all these atoms were so equally spaced and aligned that they basically
very equally spaced.
They were in the most stable form they could be, and that's why they were in a singularity, because since they were in the most stable form, everything attracted each other, and so it went down into the most tiny point. Although we call it a tiny point, I think it's because since space didn't exist, because space was defined by how many atoms there were and how wide and how. Wait, let me try and phrase it well. How they interacted with each other relatively.
Yeah.
So, for example, since all the atoms acted equally upon each other at that time, since they were all like that, space could be regarded as having no dimensions. But then something happened, and some atoms moved this way, some atoms moved that way for some reason. That was the Big Bang. And they got a sort of displacement. So since these atoms moved that way, and those atoms moved that way, they needed to sort of preserve the equilibrium they were in. So that created the law of equal and opposite force, because everything had to remain in a sort of big equilibrium. But then, because there were so many little atoms, well, at the time they were the most simple things, which I assume are quarks, I don't know. But since they moved away from each other, lots of little things started happening. Like, for example, just a simple thing like these atoms hitting each other would completely disturb the whole system. And so, since those had to hit each other, these had to hit each other, and then it would just result in what we regard as chaos, but was actually a structured sort of
collapse.
Yeah. And so space formed, which was basically space is defined as the, well, I think it is the chaos between the atoms and the ways in which they're all trying to get back into their original position in the universe.
Oh, Professor Waleed.
Yeah.
What does it have to do with gravity?
No, I'm going to explain it. So, since all these atoms had to move apart, there needed to be some sort of force pulling them back into their equilibrium state, because since they all want to get back into that state, that's the most stable state, the combined force of all these atoms results in, if one atom goes over there, all these atoms want to attract it, but that atom isn't actually being attracted, these atoms are being attracted to it too, so it's sort of just trying to restore the equilibrium between them. And we call that force gravity, which is trying to get everything back into its structured order. And now that all the atoms, what are now atoms, since they've combined in weird ways, have spread out over the universe
And made Jack.
There's mini equilibria which are forming, such as in the Earth. Pretend this is the universe.
Wow, six
Yeah.
atoms?
The Earth sort of has its own small equilibrium, since there's so many atoms, it's entirely impossible for everything to be in exactly the right position for everything to come back into the original equilibrium. Although I think that's what would happen if the universe were to end. So everything would collapse again back into the original equilibrium. So this Earth has equilibria, and it's acted upon by the force which is trying to pull every atom back into its original position relative to the other atoms. So therefore we have attraction between the sun and the Earth and everything, and big masses attract better than small masses, because big masses are formed of more of these tiny things, although there's weak forces between between small things. If all these atoms are acting upon that one to pull them back, then there'll be a large force between that and that, and it's vice versa for that one. So it just depends on how many atoms there are. So there's a constant force between any two smallest atoms in the universe. And the theory of why atoms are so small also explains why everything is quantized. Because if atoms only have a set length, then you can't actually move like half an atom's width. Not an atom, sorry, a quark. Half a quark's width, because you measure the quarks with the actual. Well, you couldn't measure quarks because you need a quark ruler or a smaller than quark ruler.
Okay.
So at that scale, these actually define space, and the relative attraction between them defines what we call as the measure. But on a macro scale, we see that as space. And so as we move through time, these atoms will gradually become, since everything's attracting everything else in the universe, trying to get it back into its original position, the singularity that started it all, eventually we'll get to a point where the forces that originally caused all this expansion are overcome by the overall force trying to pull it back, and so the universe will stop expanding and everything will stop moving apart, and it will start to collapse back. And that attempted restoring force is due to gravity and electrostatic forces on a small scale, and eventually we'll come back to this, and maybe a new universe might form. Yeah. Well, Jack, you'll be part of it.
Okay.
So yeah, that's the
I only have a quick question about your original picture of the singularity.
Yeah.
Why was that the most stable form for those?
Because all the atoms acted on each other equally.
But why did they act on each other?
Because everything was held in. So pretend you had any two atoms. Since there was no space, an atom here and here, or because there was no space, would be exactly the same as an atom here and here. So they're effectively all in the same position. So they have no dimensions. So everything had the same forces acting between them, pulling them together and holding them in the equilibrium of the singularity.
Okay.
So does that explain it?
Kind of.
So that they were all equally acted upon by each other, and they were all there at the same time, but not. They were all separate, but in the same position, because there's no such thing as position. It's just something due to forces between other objects.
Okay.
How does your model explain the fact that the universe is expanding at an ever-increasing rate?
Yeah.
So I can kind of understand that. I really like this, that gravity is a kind of force that's trying to restore order.
Yeah.
But so if you differentiate entropy, think about physics, if you differentiate the entropy equation, you get a positive gradient to it, which shows that entropy is forever increasing.
Yeah.
And also the universe it's not slowing down.
Yeah. The thing about that is, you know, the universe is expanding to infinity. That thing I was talking about 0 over 0 in the same day. There's this thing in a book called Göbel by Douglas Hofstadter, which explains strange loops and how.
Yeah, I've heard about that.
Yeah.
Have you read it?
Yeah, I'm reading it at the moment. So, like, if you start here and continuously move further and further away, you'll somehow end up at the same point. And
that assumes a particular curve to space-time, doesn't it?
yeah. So, in terms of that, if you regard our position right now as 0, and the furthest position in the universe is infinity, if you take an equation, f of x equals x over 0, and then you say that y equals x over 0, then y times 0 would be equal to x, but anything times 0 is equal to 0, so x must equal 0, but y could be anything, then that function isn't valid because it's a many-to-one function, which doesn't exist or it's not defined in maths. So, but you can also rearrange that saying y equals x over 0, and since x is 0, y equals 0 over 0, so 0 over 0 isn't defined. But you can solve that problem by regarding 0 is equal to infinity. I wrote a blog article about it. If you want to, bring it.
The interesting thing about the many-to-one function not being defined is that's just a mathematical construct. So they're there and they exist, but in maths is said we don't like that.
Yeah.
So we're not going to let it happen. So they do exist. It's like 0 over 0, like you were saying.
Yeah. So
maths
0 can take any value basically, but in my blog, in the article, I sort of suggested that 0 is equal to infinity in some way.
So, relating this back to
It's
your...
lifephysics.blogspot.com. Life.
So, relating this back to your original model,
Yeah, .blogspot.com.
your theory is that the force of it, the expanding universe, is the equilibrium force from the other way around, back from infinity. If you see space-time as one of these strange loops where instead of going on forever, it just cycles back around.
Yeah, it cycles back into the middle. So in an
we are
infinite
headed
amount
back
of time.
to equilibrium, just the other way around.
Yeah. So in an infinite amount of time, you'll come back to the original equilibrium because everything will be in a perfect position again. Because I've got so far apart that space doesn't matter anymore, and they'll come back together.
Just as when it didn't matter in the first place.
Yeah.
That assumes a particular shape of space-time, though.
Yeah. So.
Nice, Waleed. Thank you.
Can you press watch me on YouTube?
No.
Oh no, don't.
Is that what
I'd love to. I'm interested that you call it life physics. And it's just math. Got Bailey and I were arguing about this yesterday. I'd like to link your blog on Firefly.
All right.
Will it always be science, or will it be crude stuff up there?
It's sort
Look
of
at what
like
year 7 kind of.
it's sort of like psychology, physics, and maths. Like
When I get going on Firefly, can I put it up there?
yeah, that's all right.
I'd love to do that. Cool. Do you know what I really like about that is that was really good. Thank you.
Normally,
That's how science
put it on
happens,
physics
isn't it?
at CSM.
It's kind of the